Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 26. We are talking about the solidification time of a casting, particularly a sand casting with a certain temperature boundary condition illustrated, and then we found out that the total amount of time that is really needed is defined by this particular equation here, given as equation 1 probably, okay, which talks about how the heat rejected is going to be transferred across the mold face into the mold. So in other words, the solidification time Ts obtained by equating the heat rejected Qr to the heat flowing across the mold face Qt0 at Ts is twice Ak times of theta f minus theta 0 root of twice Ts root of Ts divided by root pi alpha, and that is equal to rho m times of V times of L plus Cm rho p or theta p minus theta f, okay, or the total time of solidification Ts can be proportional to the volume per unit area square or the square of the length dimension, okay, and this gamma here right here is a constant which is generated from this particular equation, okay. So in any event, let us just do how we arrived at it. So obviously the Ts in this particular case could be root of Ts in this particular case could be recorded as rho m V L plus Cm theta p minus theta f divided by let us say into root of pi into alpha divided by twice Ak theta f minus theta 0, so on and so forth, or I can say Ts is equal to rho m times of root pi alpha times of L plus Cm theta p minus theta f divided by twice k theta f minus theta 0 square, okay, times of V by A square. So this exactly is what I mean by gamma. It is a material property which depends on the thermal conductivity of the mold, the density of the liquid metal, the specific heat capacity of the liquid metal, and the latent heat of fusion or solidification of the liquid metal. So therefore it's constant, and then the solidification time here can be assumed to be proportional to the square of the length parameter V by A, volume by area, that is the length, okay. So having said that, it should be noted that the foregoing analysis assumes a plain metal mold interface AB, okay. It is usually not encountered in engineering practice because obviously there are seldom situations where there is actually a straight metal face, rather the metal that is being cast off are of different sizes and shapes, like it can be a spherical ball that you are producing, or maybe it can be a concavity or a convexity on the surface that it could be. So often we are required to find out the freezing time of complex contours in case of actual metal solidification process, and for such contours we all need to do is observe without any precise calculations the following basic features to know whether the analysis has given an underestimate or an overestimate of the actual freezing time. So observe these features. We considered 3 different types of mold metal interfaces, namely the convex, which can be recorded here, a plane interface which we have already done as is used in our analysis, and a concavity which is here. So in this particular case, as you can see that the heat flow is more divergent in nature, okay, in the convex, right, because this is how the hot metal is placed, and you basically trying to radiate the heat, or sorry, conduct the heat outside in the mold in a divergent direction, okay. Similarly, in a concavity you have the other way around, that means all the heat is being focused into a different, into one particular region, so therefore it is convergent, okay. So thus the freezing time in such cases particularly if it is more divergent, the rate obviously would be somewhat more than had it been a straight case, right, because obviously you are letting out the heat flow onto a larger volume. Okay, so therefore you can say that with the time of analysis that we had in a planar case, this would be a little overestimated. The freezing time in such a case would be kind of overestimated, okay, because freezing would happen earlier in case the heat flow is divergent. But if the heat flow is more convergent as in the concavity case, so obviously we are underestimating, so it is consequently somewhat less than that in figure P. So therefore the freezing time has to be different, at least intuitively that is what we can look at and see from these different shapes here, that how the convexity or concavity may be able to underestimate or overestimate the freezing time. Okay. So the quantitative results which are of the effect of the mold casting interface on the freezing time, they can be obtained for some basic shapes, and I am not going to go into the thermal engineering theory behind it. I am going to just mention it as thumb rules which you could actually follow to do the designing, which is the more important part here, right about here. So before we gave these results, we defined two non-dimensional parameters, namely one parameter we define is beta, which is actually equal to V by A times divided by root of alpha Ts, where V is the volume, A is the area, alpha is again the thermal diffusivity, K by rho C of the mold, and Ts is the time of solidification. And the other parameter that I would like to define is lambda, which is actually given by theta f minus theta 0 divided by rho m L dash, okay, rho C, where rho and C are the density and the specific heat capacity of the mold, whereas rho m is that of the liquid metal and L dash is the latent heat of solidification of the liquid metal. And this L dash is something which can be related to the difference between the pouring and freezing temperature, and this is basically the term L plus Cm theta p minus theta f that had been earlier illustrated in the last analysis. Okay. So this is a modified latent heat because of some issue of a higher pouring temperature than the freezing temperature. Okay, so some heat loss is by virtue of that for the pouring temperature changing into the freezing temperature, and the other part is because of the solidification, which is completely done by latent heat. So obviously if this theta p and theta f were to be equal, then L would be equal to L dash. So that is how we would estimate. So in terms of these parameters, now let us write the equation that we had seen earlier. So we on one hand had twice AK theta f minus theta 0 divided by root of pi alpha times of root Ts, that is the heat total rejected across the mold face, and the other one was related to the solidification process. So density of liquid metal times of the volume of the metal plus the modified L dash, so L plus Cm theta p minus theta f, which was actually the modified L dash. Okay. So in other words, I can arrange these terms together as V by A root of alpha Ts equals twice K theta f minus theta 0 divided by root of pi alpha rho m L dash. So we know that for the mold, the alpha thermal diffusivity is actually K by rho C, where K is the thermal conductivity of the mold and rho and C's are the density of the mold and the specific heat capacity of the mold. So therefore the beta value here can be recorded as the V by A root of alpha Ts, which is actually the parameter beta that has been illustrated here, and the V by A value again actually is nothing but this, right. So this can be written down as twice K theta f minus theta 0 divided by root of pi alpha rho m L dash. Okay. So that is how beta can be defined, and the theta f minus theta 0 by rho m L dash, this whole value times of rho C. Okay. So if I were to multiply this with, let us say, just by mentioning or by just expanding this term alpha as K by rho C, I could actually be able to write this down as the k cancels out, we have twice theta f minus theta 0 times of rho c divided by root of pi rho m L dash. Okay. So this guy is nothing but lambda, as you can see from this equation right here. So we have a case where beta can be defined in case of plane geometry as twice by root pi lambda, twice lambda by root pi. So this is in case of planar geometry, and the only difference that the concavity and the convexity would be made will be actually in terms of these relationships, and I am going to empirically now just state all these relationships without getting into the nitty-gritty of proving details. In fact, if you need any details about these expressions, you can actually ask a separate question and maybe we will send you, in the interest of time, the complete details. But for an infinitely long cylinder, the relationship that would be given is beta equals to lambda times of twice root of pi plus 1 by 4 beta, and for a sphere which are generally the shapes, more or less, this expression would be beta equal to lambda times of twice by root pi plus 1 by 3 beta. Okay. So that is how we are going to record for cylinder case and sphere case, and overall for a planar geometry this is what it is. So this is a planar geometry. So these are the three presumptions 1, 2 and 3 that we would have for us to be enabled to do problem solving, as I will illustrate in the next question. So here, for example, there is a large plate of cross sectional area A which is being cast, and I would like to numerically now start estimating the time of solidification. So you have to establish a relationship between the time after pouring and the distance of solidification front from the mold face, assuming no superheat. So we assume the pouring temperature is the same as the freezing temperature. So during the solidification of this plate shaped casting, most of the heat is rejected through the other 4 faces. Okay. And you can see that is kind of negligible. Okay. So you can see that most of the heat is rejected across the faces A, and the other faces here or here are very, very small, so their rejection rate is probably not considerable here. So the solidification front starts moving mostly in both the directions, either in this direction or in this direction, because obviously most of the majority of the heat flow is in this direction. And if the solidification front moves through a distance, let us say delta t, at some point of time t or at some instant of time t from the respective mold metal interface, then the heat rejected by each solidified half will be now estimated as QR equals rho m times of A times of delta as a function of t times L. Obviously the L dash is L here because theta p and theta f are same. We are assuming that the temperature has been, the pouring temperature is nothing but the freezing temperature. So the L dash term, which was either L plus Cm times of the difference between the thetas, that is the theta pouring minus theta freezing, this would actually be the 0 component, and L dash and L will be similar to each other. So therefore it is only the heat of solidification which actually comes out and it has to be rejected. So L is the latent heat of solidification. Okay. Now the time taken to reject this much of heat through the mold face of the area A, let us say this is T, okay, then the QR, that is the heat rejected, should be equal to twice AK times of theta freezing minus theta 0, which is the other end of the mold temperature, divided by root of pi alpha times of root of T, where T is the total time that is needed. Okay. So therefore we can always say that the total amount of heat rejected which I had earlier calculated here, that is rho m A delta L, is equated to this particular amount of heat that is actually rejected. So this is the heat translated for solidification to happen, this is the heat which is rejected, they are equal to each other, and so therefore we can say that rho m square A square delta square L square equals twice A k theta f minus theta 0, this whole thing to the power of 2 divided by pi alpha times of T. Alpha is equal to k by rho c, and it would therefore mean that the total time that is needed for the whole process here to happen is actually equal to rho m square A square times of pi alpha times of L square divided by twice A k. Let us say we just take out the square of A. So we have A square times of twice k theta f minus theta 0 whole square. Okay. So I am just doing the algebraic calculation here for the purpose of T, and these guys go off and we are left with actually a term rho m square pi alpha square of L delta square divided by twice k theta f minus theta 0 square. And supposing then the theta p were not equal to theta f, or the pouring temperature was different and there was some degree of superheat, I would say that T then in that event would be written down as Pm or rho m times of root pi alpha times of L plus Cm theta p minus theta f, that is L dash value, okay, divided by twice k theta f minus theta 0 whole square, okay, times of square of delta. In other words, that is what the gamma is going to be, and T is actually equal to gamma times of square of delta, or delta T as a function of the time of solidification becomes 1 by root gamma times of root T. Okay. So that is how the functional relationship would be obtained between the time after pouring and the distance of solidification front of the mold face. So the delta as a function of time is root of T by gamma. Okay. So that is how you do these questions. So I will actually close on here in the interest of time. So with this we would like to end this particular module, and the next module we will do a few more numerical problems regarding this estimation of the time of solidification. Thank you.